Hi. In this video, we are going to look at basics of inequalities. This is the next section in our Maths Olympiad training course. The previous section was obviously the one on functions and properties. So I hope you have understood that part and we'll continue with inequalities. This is not going to be the last time we discuss inequalities in the course. We'll come back to inequalities at a later stage. But right now, we are just introducing some basic inequalities. So before we discuss some problems, I would like to outline some of the standard inequalities that you need to be familiar with. The first one is the simple inequality a square plus b square is greater than or equal to 2ab. This is obvious because a minus b whole square is greater than or equal to 0. The second inequality is the three-dimensional analog of this a square plus b square plus c square is greater than or equal to, you can say, greater than or equal to ab plus bc plus ca. AB plus BC plus CA. Again, the proof of this is pretty obvious. When you take it to the other side, you can write it as half of A minus B whole square plus B minus C whole square plus C minus A whole square greater than or equal to 0. So this is also important. Then we have the AMGM inequality, AMGM, and this can be generalized for two variables or for three variables. So if we have two positive numbers A and B, here A and B belong to real positive, right? Then we can say that A plus B by 2 is greater than or equal to root AB. The proof of this is straightforward. You take it on the one side, take both the terms on one side, and you can show that it is equal to a perfect square, root a minus root b whole square, right? So that will always be positive. For the three-dimensional analog of this, we can say for three variables, we have this greater than or equal to cube root of ABC, right? So we will see the proof of this in a future problem in the same video. For now, we'll just write down the inequalities. Then we have Cauchy's inequality, which is also a very important Cauchy's inequality. So Cauchy's inequality states that if A1, A2, B1, B2 belong to real, then we can write A1 square plus A2 square multiplied by B1 square plus B2 square is going to be greater than or equal to A1 B1 plus A2 B2 whole square, right? This, the proof of this, you can think of it as two vectors, and this inequality basically says that A dot B is less than or equal to mod A into mod B, right? If you think of it as two vectors A and B with components of A1 and A2 for A and components of B1 and B2 for B, you know from basic theory that the dot product of the two vectors will always be less than or equal to the product of their moduli or the lengths, right? Also, by the way, for AMGM inequality, equality happens when this equal sign happens when A is equal to B, and here it happens when A is equal to B is equal to C. And in the Cauchy inequality, the equal sign happens when the two vectors are parallel to each other. Basically, we can say that A1 by B1 should be equal to A2 by B2 for the equality case. Otherwise, this is greater than this, but equal to happens when A1 and B1 are proportional to A2 and B2, right? Now, we can also generalize Cauchy in three variables. So in that case, we can say A1 square plus A2 square plus A3 square multiplied by B1 square plus B2 square plus B3 square will be greater than equal to A1 B1 plus A2 B2 plus A3 B3 whole square. Again, you should think of them as two vectors. A vector is A1 I cap, for example, A2 J cap, and A3 K cap. And again, B vector can be written as B1 I cap plus B2 J cap plus B3 K cap. And this inequality is again saying mod of A square, mod of B square is greater than equal to A dot B whole square. That is an obvious fact because the dot product is defined like this. A dot B is equal to mod of A mod of B cos theta, where cos theta value will always be less than equal to 1. So A dot B will be less than equal to mod A mod B. So that is what this Cauchy inequality is saying. When is the equal sign happening here? When the two vectors are parallel to each other, or when you can say that the components are proportional. So A1 by B1 is equal to A2 by B2 is equal to A3 by B3. That is when the inequality becomes an equality. Then we have the triangle inequality. So triangle inequality is pretty straightforward. We will look at the geometrical interpretation of this, but usually it is written like this: mod of A plus B is less than equal to mod A plus mod B. And equality happens when AB have the same sign. AB is greater than 0, then equality. So basically, if both A and B are positive or if both are negative, then you can get an equality. Otherwise, it's an inequality, right? Similarly, you can also say that mod of A minus mod of B is less than equal to mod of A plus minus B, less than equal to mod of A plus mod of B. So this is the generalization of the Cauchy triangle inequality. Another variant of this sometimes is useful. We can say A minus C is equal to A minus B plus B minus C is, and that will be less than equal to mod of A minus B plus mod of B minus C. That is basically splitting A minus C like this and saying that it is less than equal to these two, right? And finally, we look at the two-dimensional version of this triangle inequality. We can say for any real numbers x1, y1, x1, x2, y1, y2 belong to real, we can always say that root over x1 square plus y1 square plus root over x2 square plus y2 square will be greater than equal to root over x1 minus x2 whole square plus y1 minus y2 whole square. So this is a 2D version of the triangle inequality. And if you want to understand it, we can just draw a simple graph. This is the xy plane. And if you have one point here, which is x1, y1, and another point here, which is x2, y2, then what are these terms? These terms are root over x1 square plus y1 square and root over x2 square plus y2 square is basically the distance of these points from the origin. So OA and OB is this. So we are saying OA plus OB is greater than equal to, what is this? This is AB. OA plus OB is greater than equal to AB. So basically this means that the sum of the two sides of the triangle is always going to be greater than equal to the third side. So that is the triangle inequality in two dimensions. Now let's look at some problems, a few questions here, so that we can apply these identities. The first question is this one. If ABC is greater than 0, we have to compare the numbers. Compare the numbers, basically tell which number is bigger, A power 2A, B power 2B, C power 2C, and A power B plus C, B power C plus A, and C power A plus B. So usually when we have numbers that we have to compare, or we have to compare two algebraic expressions, there are two techniques that you should be familiar with. One is comparison by ratio and one is comparison by difference. So comparison by ratio is basically if you have positive numbers A and B, and if you want to compare which one is bigger, you can take the ratio of A by B. Here what we will do is do comparison by ratio. So we can divide this by this because all of them are positive. So we can say A power 2A, B power 2B, C power 2C divided by A power B plus C, B power C plus A, and C power A plus B. And that can be written in a simplified form as A power 2A minus B minus C multiplied by B power 2B minus C minus A and C power 2C minus A minus B. And you can even further simplify it a little bit and write it as A by B to the power A minus B and B by C to the power B minus C and C by A to the power C minus A. You can check it out. This is actually equivalent to the previous statement, right? Now, how do we go about understanding whether which one is bigger or not? We have to check whether this ratio is greater than 1 or not. So in this case, ABC are all positive. So without loss of generality, we can assume that A is greater than B is greater than equal to C, which is greater than 0, right? So that means that A by B is greater than 1, B by C is greater than 1, and C by A is less than equal to 1, right? So also that also means that A minus B is greater than 0, greater than equal to 0, B minus C is greater than equal to 0, and C minus A is less than equal to 0, right? So that implies that A by B to the power A minus B, you have something greater than 1 raised to the power positive. So that will be greater than 1, right? Similarly, B by C to the power B minus C. Again, something greater than 1 raised to the power a positive exponent. So that will be greater than 1. And then you have C by A power C minus A, where C by A is less than 1, but C minus A is negative. So when it is negative, you will have to take a reciprocal of that, and that will become a positive quantity greater than 1, right? So for example, 0.2 to the power minus 1 will become 1 by 0.2, which is equal to 5, which is greater than 1, right? So whenever you have a fraction which is less than 1 and you are raising it to a negative power, the answer will obviously become greater than 1. So that shows us that each of the three terms here are greater than 1, which implies that this ratio is greater than 1, which tells us again that this number is bigger than this number, right? So we have been able to successfully compare these two, and the technique we used was comparison by difference, or comparison by ratio. I will show you an example when we do comparison by difference. So this is question 2. So let A, B, C be positive real numbers, be positive reals such that, and we have to show that A cube plus B cube plus C cube plus 3ABC is greater than equal to AB into A plus B plus BC into B plus C plus CA into C plus A. So again, here the technique that we'll use is to compare these two by difference. So we'll try to find out LHS minus RHS, and we have to try to show whether it is greater than 0 or lesser than 0. So before we do that, however, we can assume without loss of generality, we can assume that C is the minimum out of ABC, minimum of A, B, and C, right? And C is positive. We are assuming that C is the smallest out of A, B, and C. And now we do LHS minus RHS. We will say A cube plus B cube plus C cube plus 3ABC. We have to do minus AB, A plus B, minus BC, B plus C, minus CA, C plus A. And now we'll rearrange it nicely, and we'll rearrange it in a certain way in order to get the sign correctly. So try to follow this step. We'll be basically grouping the terms together. So A cube plus B cube, and then we'll subtract minus AB, A plus B, and we will keep 2ABC here and subtract minus C, A square plus B square. So think about it. Which terms have we taken? We have taken 2ABC out of the 3ABC. We have taken this whole term, right? And we have taken CA square and CB square. Where was CA square and CB square? It was here. CA square was here, and CB square was here, right? We have taken the first two terms of these, right? And what is left for us now? What is left is basically C cube. C cube was left because we have already taken A cube plus B cube here, right? So C cube, one ABC was left, C cube plus ABC, and then finally the last two terms were left, which is C square B and C A square C, right? Minus basically C square common, we have A plus B, right? What is left here? Let me just confirm this. We have taken here CA square, CB square, CA square. Okay, we have taken the second term. So C square A was left, right? C square A was left here. We have not taken the first term here. We have taken the second term here, right? So C square A was left here and C square B was left here. So C square A plus B is left over, correct? So if you group it like this, you will realize that here we can take A plus B common, a plus b common between these first two terms, and you will get a square minus ab plus b square minus ab. Plus here we can take c common and you get 2ab minus a square minus b square, right? So this is the first bracket. You can see that this is becoming a minus b whole square, and this is already minus of a minus b whole square, right? So we can take a minus b whole square common and we'll get a plus b minus c, right? Plus here what can we do? We can say we can take c common throughout. It becomes c square plus ab minus a c minus bc, right? And then we can take common here c common c minus a plus b common a minus c. So we take a minus sign and we take c into c minus a and we'll get c minus b. So this term is coming as plus c into c minus a into c minus b. Now the question is over because this is positive. A minus b whole square is positive. A plus b minus c is going to be positive because we already know that the c is the minimum out of a, b and c. So obviously b minus c is positive. So a plus b minus c is positive. So the first term is completely positive. C is positive. C minus a is negative. And c minus b is negative. So negative negative becomes positive, and this whole term is also positive, right? So we are getting something positive plus positive here. So that means our LHS minus RHS is basically becoming positive, and that means we have shown that the LHS is bigger than the RHS. Now, how did I do this? The main idea here is just a correct grouping of terms. You could probably group it in a different way also and prove the same thing, but that I will leave to you. You can try that out yourself. The main technique that we have shown here in the first two examples is comparison by ratio and then comparison by difference, right? Let's look at the third one. This is suppose A and B are real numbers with mod of A less than equal to 1 and mod of A plus B is less than equal to 1. We have to show that minus 2 is less than equal to A plus 1, B plus 1 less than equal to 9 by 4, right? So we will approach this problem in a slightly unique way. We have seen this technique before in the previous sections where we try to look at a monotonic function and try to establish identities on a monotonic function. So what we'll do here is we'll say let t is equal to a plus b. Now it is given to us that mod t is less than equal to 1, right? Now a plus 1 into b plus 1 will become basically a plus 1, and we can write b as t minus a, right? B can be written as t minus a plus 1, right? So the quantity that we want to find out the upper and lower bound for a plus 1 into b plus 1 can be written like this, right? And if you think about this, this can be called a function of t where t is equal to f of t is equal to a plus 1 into t minus a plus 1, and this is a linear function of t, and the coefficient of t is a plus 1, which is greater than equal to 0. This is the coefficient of t in this linear function. The other term is going to be constant. So this is the coefficient, and a plus 1 is greater than equal to 0. Why? Because mod of a is less than equal to 1. So it can only be between minus 1 and 1. So minus 1 and 1, if something is between minus 1 and 1 and you add 1 to it, obviously it will be greater than equal to 0. So it's a linear function of t with a positive coefficient. That means f of t is monotonically increasing. So now if it is monotonically increasing, then we want to find the maxima and minimum values of this f of t, right? So then we only have to check the endpoints, right? We can only check the endpoints of the interval. So what are the endpoints of our interval? we know that mod t is less than equal to 1. So t varies from -1 to 1, right? So we only have to check f of -1 and we have to check f of 1, right? The end points of the interval will give us the maximum and minimum values of f of t, right? So if you think about that, what is f of 1? F of 1 is basically a plus 1 into 2 minus a, right? F of 1 is a plus 1 into 2 minus a. If you simplify that a little bit, you will get 2 plus a minus a square, right? 2a plus 2 minus a square minus a. So 2a minus a becomes, yeah, this is correct. So this can be written as 2 plus 1 by 4 minus 1 by 4 plus a minus a square, which can be written as 9 by 4 minus a minus half whole square, right? So we are getting f of 1 is less than equal to 9 by 4, right? Since f of t was monotonically increasing, f of 1 is possibly going to give us the maximum value of the f function, right? And f of 1 is less than equal to 9 by 4, and it is f of 1 can be equal to 9 by 4 when a is equal to half, right? So that should be the maximum value of our f of t on this interval, right? So we have basically found the upper bound of f of t, right? Now for f of minus 1, what is f of minus 1? F of minus 1 comes out to be a plus 1 into minus a, which is basically minus of a square minus a. And f of this value can be the lowest possible value of this will be minus 2 when a is equal to 1, right? That is obvious. You can just look at it because a goes from minus 1 to 1. It is obvious that the lowest possible value of this will be minus 2 when a is 1. So f of minus 1 was supposed to give us the lowest possible value of our function, our monotonically increasing function. And we have found that the lowest possible value of f of minus 1 is minus 2 when a is 1. And the highest possible value of f of 1 is 9 by 4. So we have basically found out the range of this expression, right? So we can say with certainty that minus 2 is less than equal to a plus 1 into b plus 1 is less than equal to 9 by 4. That is the upper and lower bound for this expression. So this is a non-standard method to find maximum minima. You should learn how to apply this. We have seen this technique used 2-3 times before in the previous videos. So if you go back and try some of the questions that we have discussed, you will be able to quickly grasp this technique. Always be on the lookout for spotting a monotonic linear function. And then if they can spot a function like that, then you only have to worry about the endpoints to check the upper and lower bounds of it. So that's it for this video. In the next video, we'll be looking at the basic problems that use the AMGM and the triangle inequality and the Cauchy's inequality, the inequalities that we had listed down in the beginning of the class. And we'll be looking at some more practice problems on those. So stay tuned for the next one. I hope you got something from this video.